Hi everyone, my name is Lohit.petikam. I'm a researcher at Computational Media Innovation Centre at Victoria University of Wellington in New Zealand. This work proposes a new way to control art-directed 3D appearance based on lighting environment using a latent space. To start, we need to understand the concept of look development, or look dev. This is the task of verifying a character's appearance across a range of background lighting environments. Notice how each lighting environment gives very different appearance on the character. Highlights and shadows have a different quality depending on the lighting conditions. Right now, artists are stuck tweaking a single material setup that must look artistically good in all lighting situations. And this is really hard, and it's not always possible. That's why in traditional film and animation, it's very common to cheat the lighting to meet the aesthetic needs of the director. This kind of lighting is heavily motivated on the character and story rather than physical laws or the true environment. And I think these images make it pretty clear that lighting in film and TV is highly contrived no matter what the background is. For example, a director might look at this scene and tell a junior lighter to add a rim light here. We can place artificial light behind a character, and the director maybe likes the way it pops out of the background. But in this overcast sunset scene, the rim light might be too strong, so we can turn it off here. But we also notice that the highlights on the skin have diffused away because of the softer lighting. You can cheat again here to bring back some details, but when we go back to the sunny scene, the highlights don't look as clean, and we've also lost the rim light that we wanted here in the first place. So we start to see the problem that edits for one scene are not compatible in other scenes. In offline film production, this might be okay because artists could make edits for the few number of scenes occurring in the movie and just turn them on and off when needed. But for real-time games and AR, these environments aren't known beforehand. They're widely varied, and it's not like the art director can make all these unique artistic decisions for every possible environment. If we turn to previous work, art-directable rendering papers let you cheat the lighting, but only for one scene. You'd still have to manually do different edits when the lighting environment changes. There are some few works that try to preserve user-made edits when lighting features just slightly change. However, these couldn't handle the drastic lighting changes when going from, say, indoor to outdoor or from sunny to overcast. The way we propose to solve the problem is to use environment map latent space for look dev and art direction. Here, during the look dev stage, artists navigate our learned 2D embedding of environment maps with semantic clustering of indoor, outdoor, and overcast scenes. For the clusters where appearance editing is needed, artists can paint directly on the space to art direct material and lighting as desired. In this case, artists can paint high gloss values specifically for cloudy scenes where highlights are diminished. Here, synthetic rim light has been boosted specifically for sunny scenes and dimmed in the sunset scenes, and then its transition from sunset to sunny is finally controlled through painting. We encode new environments which weren't seen during training into the same space, and then for this new location we can sample the art-directed appearance parameters from the painted images. In this way, interactive applications can automatically apply the intended character's appearance whenever the lighting changes. The latent space component of this is crucial to make this workflow possible. It needs to have clear semantic clustering, so we aim to embed in 2D with no overlaps or inclusions, and also clear transitions between the clusters. Achieving this lets artists have greater freedom of control to control the look of their characters in many lighting situations. We use dimensionality reduction to embed a dataset of environment maps containing various lighting environments. Specifically, we use UMAP, which is a manifold learning technique, to embed the dataset in 2 dimensions. So how did we arrive at this embedding? We first took a dataset of environment maps of various indoor, outdoor, sunny, overcast, nighttime scenes, and after collating these from existing environment map datasets, we sample a balance between indoor and outdoor scenes, arriving at a training dataset of 350 samples. Before extracting any lighting features from these, we want to align the data. Environment maps can be rotated horizontally without changing the lighting quality. So we align all the environment maps by their dominant light's horizontal angle. We first detect the dominant light in the radiance map, by simply filtering noise and finding the highest peak. And then we center align all environment maps around this peak. We keep the dominant light elevation varied because this is correlated with other lighting properties. For example, if a sun is low in the sky, it would create atmospheric scattering and changing the lighting quality. The first environment map feature we learn is spherical harmonics. And although these are a low frequency environment map representation, we use them to remove image and texture details. We compute the components up to the 5th band, which we find is good enough for detecting between hard, soft, and multiple lights in an environment. We also normalize the coefficients with their L2 norm to account for different brightness scales between these environments. And although spherical harmonics was computed in RGB, we needed to differentiate environment map color as a way human perceives color. So we added the mean color of the environment map in LAB color space as another feature appended to the spherical harmonics. We divide these LAB values by 100 for comparable numerical ranges with the spherical harmonics. And then we use UMAP to compute the embedding based on the L2 distance between the combined feature vectors of each environment. Before we do this, we still need to choose how much importance do we give on this mean LAB color compared to the spherical harmonics. Because if we weight spherical harmonics to be more important, then we find many indoor samples, which we've circled across the warmer colors here. They are embedded too close and overlap with the outdoor scenes. But if we weight LAB too high, we do get clearer color separation, but we start to lose important clustering of lighting properties. So we experimentally found that a weight of 0.32 was good to give us clear separation of an indoor cluster, and also we still keep the clusters relatively close so that artists can still define unique clusters, unique art-directed appearance for different clusters and between them as well. So this is the final embedding. We can interpret some learned clusters and dimensions. The most obvious one we observed was that it embedded environment maps with decreasing light elevation from left to right in the space. And we also see 3 main clusters emerge, spread vertically across the space. From top to bottom, we've got an outdoor overcast cluster, and an outdoor sunny, and an indoor cluster at the bottom. So now that we've organized environmental lighting in a 2D visualization, artists can now assign appearance parameters for each of these clusters. In this example, a texture was made to art-direct the glossiness of the skin, and then high gloss values were painted in the overcast cluster. The rest of the image had the default glossy value. So what this means is that in cloudy environments, the character will have boosted highlights, and for any other environments, it will remain the same. UMAP simultaneously learns the encoder while training the embedding. So when deployed into interactive applications, we use this encoder to embed new environment maps into the same latent space. We use this latent coordinate as the texture coordinate to sample the painted images. The renderer just needs to update the lighting and material with these sampled values. Now this procedure only works if the new environments get embedded into the right cluster. So how do we know if this will happen in the real world? Well, we evaluated how well unseen environments get encoded into this space. We collated a test set using 262 outdoor and 80 indoor environment maps from the same vendors that we used for the training set. We then manually labeled them to observe where the clusters form. When we embedded this test set, using the encoder that UMAP learned during training. We just had to calculate the same spherical harmonics and LAB features. Here we see that the test set was embedded with the same clustering observed in the embedding. And it also, again, consistently with the embedding, ordered the environment maps from left to right with decreasing light elevation. There is some noise and outliers between the clusters, and we attribute this to the stochastic nature of the UMAP algorithm. We also include some of these night sky scenes just to see what would happen. They don't really form their own cluster because they were pretty rare in the training set to begin with, but they do consistently fall in some outdoor cluster. We also made another test set using 156 environments from the HDRI Haven dataset. These had much higher dynamic range than those found in the test set. For the outdoor clusters, we see much clearer clustering beside the two outliers out at the bottom. And we think this is because they had much higher dynamic range than those seen in training, and therefore UMAP was able to easily distinguish between sunny and overcast. In summary, we propose a new workflow for artists to define how their character is stylistically lit in varying lighting conditions. We achieve this by encoding general lighting semantics in 2D and allowed artists to paint how the renderer should art direct the look of the 3D character across many lighting conditions. We are still limited by the encoding accuracy and lack of nighttime scenes. In future, we'd like to use semi-supervised learning so that we can incorporate labels into the training process with the hope of achieving better clustering, clearer clustering, and better encoding accuracy. We'd also like to train with richer data sets so that we can obtain more clusters such as the nighttime scenes. That's been it from me. Thank you very much for listening.